Hello and welcome to ChemVid. Today we're going to be talking about electron configurations, okay? And for these notes, we go a lot over the first part as a review, but we're going to be focusing on this part right here, how to write electron configurations. So watch the video, phosphorescence versus fluorescence, for this part right here, and then you're going to watch, or sorry, not watch, take notes for electron configurations in this video, and then we'll cover this part in class. Alright, so your homework is just to do the second page. Alright, let's get started. So first off, we need to start off with a bit of background about how orbitals work. Alright, to start off, we have s, p, d, and f orbitals. So most people are used to Bohr's model, where you have a nucleus and then you have an orbit and then another orbit, and you have 2 electrons in the first one and then 8 electrons in the outer one, and then it just keeps going. But we know now, because of Schrodinger, that our electrons don't fall on lines like Bohr said they did, but instead they have spaces or places where they can be. And he called these different places S, P, D, and F. So an s orbital actually looks like a sphere. Okay? So in reality, you have a nucleus, and then imagine a balloon around, like a pea, all right, in the middle. The balloon is where 2 electrons, 2 baby, like really tiny electrons, are zooming around, and they create a negative space like a sphere, okay? So electrons don't lie on a line or on an orbit. They're actually moving around quite fast all around the nucleus in a sphere-type shape, okay? The next orbital that we have is called the p orbital, and it looks like a dumbbell. It has 2 sides, kind of like a dumbbell, and there are 3 of them, and they face in different directions in space, okay? So one's on the x-axis, one's on the y-axis, and one's on the z-axis. And each p orbital can hold 1 electron in each dumbbell. And when you put them together, they kind of look like a flower. So I like to refer to these as petals, but in most textbooks and in most professors, they refer to them as dumbbells, okay? So a p orbital can hold 6 electrons, and it looks kind of like a flower or a dumbbell, whichever one you prefer. Whereas s orbitals, it can only hold 2 electrons, okay? And it looks like a sphere. These are the ones that you'll need to be able to draw. They're pretty simple to draw. D and F get a little more complicated, but you'll only have to draw S and P. Alright, so the next one, the d orbitals, these are for our transition metals, and it kind of looks like a 4-leaf clover. And there are 4 of them, 4 4-leaf clovers, and again, they're in different planes. So like it's in the XY plane, it's in the XZ plane, it's in the YZ plane, you know, things like that. But these are the d orbitals. There are 5 of them, and it can hold a total of 10 electrons. And then the f orbitals are far too, I can't draw them. There's far too many of them, and they're far too complicated. But these guys hold 14 electrons, okay? So s orbitals hold 2 electrons, p orbitals hold 10, and f orbitals hold 14. And here's a better drawn out picture. So you can see S is a sphere, P are the dumbbells, D has 5 that look kind of like 4-leaf clovers with a donut, and then this is an F orbital. So F orbitals are far more complicated to draw, and you'll never have to worry about them. But they can hold, they are 7 orbitals, and they can hold up to 14 electrons. Alright, so electron configurations are all about knowing where the electrons are and how they're going to react with other elements. So every orbital, or every atom, starts with an s orbital. and we draw a line to represent the orbital. So instead of drawing the shapes like circles and dumbbells and things like that, we just draw a line. And then it forms another s orbital, and we call that the 2s orbital. So the first one is the 1s, and then we have the 2s. Then the atom forms a p orbital, so a 2p orbital. And there are 3 dumbbells, remember, but instead of drawing them out, I just draw lines. And then we have the 3s, and then we have another 3p, and then we have a 3d, 1, 2, 3, 4, 5. There are 5 orbitals in d. And then you have a 4s, and then it just keeps going and going and going. 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 3d, or 4d, 5s, and it just keeps going and going and going and going. So electrons configurations can be a little tricky at first, but once you have the pattern, you got it down. So you just have to keep practicing until the pattern clicks in your mind, okay? Now, one of the things that we use to help us find these p orbitals, d orbitals, s orbitals, and know the pattern is our periodic table. So if you look at your periodic table, sorry, mine's a little squished. I don't know what happened when it copied, but that's okay. If you look on your periodic table, you can actually see our elements are organized by orbitals, okay? So over here, the first 2 groups and helium, because helium technically is supposed to be right here, but he's over there because he's a noble gas, and anyway, he's a little special, just like hydrogen. But group 1 and 2 and helium represent the s orbital, okay? And then the groups 13 through 18, except for helium, these guys represent the p orbitals. Okay, that's where these guys' electrons go into the p orbitals. And I'll show you more of what that looks like in a bit. And then the transition metals, these are the d orbitals, or the d block. And then we have the f block right down here with the lanthanides and actinides. So what this is saying is that the electrons that these elements have reside in these different orbitals based on where they are on the periodic table. So it actually makes it quite easy to write electron configurations. I'm going to take a moment and label the rows. So this is the first row, second row, third row, fourth row, fifth row, sixth, seventh, and that's good. Okay, so when you're trying to write an electron configuration, you're just writing where the electrons are. So let's start off with beryllium, okay? Beryllium has 4 electrons. And because it has 4 electrons, that means that it's going to have 2 s orbitals. So if you recall our pattern, we start off with a 1s, and then we have a 2s. And if you look, in the first row, this is the s orbital, right? In the first row, there are 2 electrons. And then in the second s orbital, there are 2 more electrons. So we write it like this. So an electron configuration is telling me which row the electrons are in, which orbital the electrons are in, and how many electrons are in that orbital. So let's go back to my other drawing and see if we can get a little more light on the situation. Let's try aluminum. So aluminum is number 13 on the periodic table. It has 13 protons and the neutral atom has 13 electrons. So what we do is we take those 13 electrons, you start at the bottom, you always start at the bottom, And then you just keep adding electrons until you run out. For our purposes, we represent electrons with little half arrows like this and half arrows like that. Okay? One goes clockwise and one goes counterclockwise. And that's because electrons actually have a spin. They actually spin around in different directions. So the arrows let us represent that spin. So in the 1s orbital, I am going to put in 1 electron and then 2 electrons. And they always go opposite ways, because if they both went the same way, they would cause friction and they wouldn't be stable. Okay? So I have 2 electrons here, and then I'm going to go here, and then I have 2 more electrons here. Now I go up to my 2p orbital. And electrons don't like to be in the same orbital unless they have to be. So electrons will actually spread out like this unless they have to have more. So since I have 13 total electrons, I'm going to have to fill up these orbitals, but they like to spread out first if they can. Alright, so now I have 2, 4, 6, 8, 10. So I have 2 more here, and then 1 more in the 3p orbital. Okay? So if you look, I have 2 electrons in the 1s, 2 electrons in the 2s, 6 in the 2p, 2 in the 3s, and 1 in the 3p. So when I write out my electron configuration, I write 1s, 2, because I have 2 electrons in there, 2s, 2, 2p, 6, 3s, 2, and 3p, 1. And that is the ground state electron configuration for aluminum. And if you look at the periodic table, you can see that aluminum, right here, aluminum is on the 3rd row. It's in the P block, and it's the first one. It's 3p1. So if you look back here, this electron configuration makes sense with what we see on the periodic table. And so that's how we write electron configurations. So this is the extra set of notes I gave you. It's not the ones you're turning in, but it's great practice to practice these electron configurations. So let's do oxygen. Oxygen has 8 electrons, and I find that on the periodic table. So whenever you're doing electron configurations, you always want to find out how many electrons total there are. In this case, it's the same as the protons because it's an atom. It's not an ion. So over here, I know there are 8 electrons total. Okay? And in this box, and in the boxes on your worksheet, this is asking for the Lewis dot structure. And we'll go over more of this in class. But basically what you do is you draw the symbol, oxygen, and then you draw how many valence electrons there is. And you guys have learned that you find valence electrons by what group the atom is in. So there are 6 valence electrons in oxygen because it's in group 16. So I am going to draw 6 dots to represent the valence electrons around oxygen, like so. And that's called the Lewis dot structure. And this structure only shows the valence electrons, whereas an electron configuration or an orbital diagram shows all of the electrons. All right? All right, so an orbital diagram is when you do the arrows. All right? So since oxygen has 8, I'm going to start with the 1s. I always start with the 1s. And I'm going to start filling them in. So there's 2, 4. And remember, when you get to a P or a D block, you've got to spread out the electrons. So 1, 2, 3. So 2, 4, 6, 7. And then I double up. So now I'm going to have 8. So oxygen's orbital diagram looks like this. Okay? orbital diagrams are the ones that have the arrows. They're the ones that we write out how many electrons are in each orbital, and we use the arrows. Whereas an electron configuration, that's the one we do with the 1s2, 2s2, 2p6, all that kind of stuff, all right? Both of them have a pattern, and you'll figure it out as you get it. So here I go. So I have 1s, 2, 2s, 2, and 2p4. So that is my complete electron configuration. Now I'd like to go over the condensed electron configuration. So if you look at the periodic table, you can see that if I were to do tungsten, okay, W, I would have to write out 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6, you know, and I would just have to keep going and going and going. And it gets kind of tedious. So what we do is we actually use noble gases to make our electron configuration smaller. So if I was going to do tungsten, this guy right here, what I do is I look for the noble gas before him, and then I put the noble gas in brackets. Oops. Come on, there we go. I put the noble gas in brackets, and then I write out 5d, 3, 4, and we'll go over D block, so don't get too concerned. And then 6s2. So as you can see, instead of writing out all of the different blocks, all I have to do is write out the noble gas that comes beforehand, and I write out what's left. So let's do that with oxygen. So oxygen is right here on the periodic table. So the noble gas that comes before him is helium. So when I write the condensed version, I am going to put in brackets helium, because helium is my noble gas, and his electron configuration is 1s2. So then I would pick up with 2s2, 2p4. So how you write the condensed electron configuration is you find the noble gas that's right before your element. You are then going to replace its part of the configuration with a bracket, and then you just write out the rest of it behind it. And so that's how you do condensed electron configurations. Alright, so an orbital diagram is the diagram that shows arrows representing electrons in the different orbitals. Aufbau's principle is the principle that you have to fill the lowest energy level first. So for instance, that's why we always start with 1s. It's because you always have to start at the bottom and move up. That's Aufbau's principle. Pauli exclusion rule is that there can only be 2 electrons or 2 arrows in each orbital, okay? And they both have to be going in opposite directions. So that's the Pauli exclusion rule. And then Hund's rule is for things like the p block. When you have multiple orbitals, we fill all of the orbitals first, and then we double up. So if I look back here, remember when we filled up 3 electrons all spread out first, and then we doubled up when we had to. So you're never going to have 2 orbitals that are full and 1 empty, because they're always going to spread out. That's Aufbau's rule. Excuse me, there we go. Alright, Hund's rule. Hund's rule. Alright, so we talked about expanded and condensed. Let's go over ground state and excited state. Alright, so here we have oxygen. And oxygen has the electron configuration of 1s2, 2s2, 2p4. Okay, so this is what we call the ground state. It's when all the electrons are in their appropriate orbitals, okay? You filled the lowest to the highest. So ground state is when electrons haven't moved. And we've talked about how electrons jump and then emit light. So when they're on their lowest energy level, that's the ground state. And then when they jump to an excited state. So if I ever ask you to write the excited electron configuration, what you do is you take an electron from your orbital, the highest orbital you have, and then what you're going to do is you're going to put it into the next energy level. So instead, what you would write is something like this. Because one of the electrons has gotten excited and jumped to the next energy level. Okay? And so now we would write 1s2, 2s2, 2p3, 3s1. And this is the excited state because it shows that an electron has moved from its original location. It's not the ground state. All right? So excited states just show electrons moving. And you can do this for any electron configuration. All you do is move one electron from the highest energy level to the next level, to the next orbital. Okay? All right. So now we've got ground and excited state. Sorry, that took me a moment. And that's all that is on your notes. So if you want, you can stop here. But there are a couple of things that we're going to go over in class that you might want to hear first here before we learn it in class. So it's up to you what you want to do. All right, let's get started with that new stuff. All right. So we're going to work on the D block. The D block has special rules. What I tell my students is that the D block is dumb because it actually doesn't follow the same numbers. It doesn't follow the row numbers that we're used to. And so I tell them that so that they remember that D is unique, okay? It's a dumb orbital, and you always have to subtract 1 from the row number. All right? So I'm going to show you what this means. We're going to do titanium. Titanium is number 22, and we're going to do it on your packet here, okay? So titanium is number 22. That means it has 22 electrons. So I'm going to fill it in the same way I normally do. 1, 2, 3, 4. All right, and now that I'm all done with that, I have filled in 22 electrons just like we normally do, okay? However, if you notice, the 3D orbital comes before the 4s orbital. So if you look at the periodic table, the D orbital, this first D orbital, the first transition metal, is actually on the 4th row. However, in an atom in real life, the D orbital actually comes before the 4s orbital. So we always name this 3D, all right? So that's why I always said subtract 1 from the row. Because even though technically this is in the 4th row, it's called the 3D orbital, all right? So when I look at this guy, my 3D orbital has 2 electrons in it, all right? Just like normal, but it's not the 4D orbital, it's the 2D, okay? And so when I write this out in my complete electron configuration, I'm going to write it out just like normal, 2p6, 3s2, 3p6, and then instead of putting 4s, I'm going to put 3d2, 4s2, okay? So D's are dumb. Transition metals are a little bit tricky. But all you have to do is remember, you fill it up like normal, and then you just put the 3D next to the 3P. All right, so as long as you remember that D's are dumb and you have to subtract 1, you'll be just fine. Okay? And then while we're here, why don't we practice our condensed version? So if I, 3p6, I'm going to look at my periodic table. So the 3rd row and then the p orbital is argon, which is the noble gas that comes right before titanium. Titanium is right here, okay? So I'm going to use argon for my condensed version. And I'm going to put argon in brackets. And then argon is all the way up to 3p6. So all I have to write down is 3d2, 4s2. And that is the condensed one. So basically with D block, it's a little bit odd, and there's a couple more rules we'll go over about in class. But don't worry, you can handle them. It's just a pattern, and once you have the pattern, you'll be off to a great start. So if you look at this practice sheet, I have all of the places written out so you can draw out the arrows and then draw out or write out the electron configurations. And it'll help you because then when you look at the periodic table, you'll be able to just spout off electron configurations just by looking at the periodic table and walking them across. But for the beginners, it always helps to draw things out. So for instance, if I was doing calcium, right here, Ca20, I'd start at the beginning. 1s, and there are 2 blocks in the 1s. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Okay? And you'll get there, you just have to practice. Alright, the rest of this we'll go over in class, and that's it for today. See you next time.